I am Diana Murphy, and I will be introducing our speaker today, Zlatko Minev, who is a research staff member at IBM Quantum, project and technical lead of IBM Quantum Device Design and Analysis Qiskit Metal Project, and the product manager and host of IBM's Qiskit Quantum Information Seminar Series. Zlatko has received his PhD with distinction from Yale University in the field of superconducting quantum physics under Michel Devoret. And recently, MIT Technology Review named Zlatko one of their 35 global innovators under 35, and his dissertation work on catching and reversing a quantum jump mid-flight was selected as the top math physical sciences discovery and discovers the top 50 stories of the year. And there are many, many more accolades for Zlatko, but just in the interest of time, I would like to turn it over to you, Zlatko, to take us through your presentation today. Thank you for joining us.
Thank you, Diana, and thank you for the invitation. And good morning to you, everyone. Thank you very much for tuning into Quantum Thursday today. Today, I'm thrilled to share some recent science results, as well as some recent results about Qiskit Metal for quantum device design and analysis. I'm Zlatko Minev, and I apologize for my long bio that Diana just shared with you. So I'll just dive right into it. I hope that what I'll present and share with you today can help make your quantum design life a little bit easier. So let's begin with maybe a little bit more about what is Qiskit Metal for quantum device design. I think, as you know, designing quantum devices is the bedrock that underlies the whole quantum ecosystem. But it's a difficult multi-step process that connects traditionally disparate worlds. Metal is automating and streamlining this process. And the vision for Metal is to develop a community-driven universal platform that's capable of orchestrating quantum chip development from concept to fabrication in a simple and open framework. The aim here is really to accelerate and to lower the barrier to innovation of quantum devices. So I'm quite thrilled to speak here today. This is really the first public talk after the recent launch of Qiskit Metal. It's generally accessible, free, and open source. I should mention everything I'll talk about is really on the web at this point, and it's licensed under Apache 2.0, which is the most permissive thing. Before I begin, I'd like to also just spend a minute to acknowledge the great work of the team here. It's grown quite a lot. I think I started this project here at IBM about 2 years ago, and since then, really the team's been growing a lot, and it's been a real pleasure to work with these folks. And a lot of the work you see has been greatly impacted. So a huge thank you to the Qiskit Metal team, Dave Mackay, and everyone else who's really helped make this happen. So about today, I'll begin with a broader picture overview and then zoom into slightly more technical work, starting with what is the big picture of designing a quantum device? What does it take to create a quantum processor? And then I'll hone in on a particular flow that we can use with Qiskit Metal in order to design from end to end a quantum processor. So we'll kind of walk through that process. And in the middle, I'll pause and present a broad overview of two recent key methods on how to design and analyze quantum devices, namely the energy participation ratio approach, which was developed at Yale by yours truly, and then the lumped oscillator model, which we've just put out on the archive a couple of weeks ago. So with that, I'll dive into quantum chip design. Feel free to interrupt me with questions during the talk, and then we'll have also some questions at the end of this talk. If you allow me to back up quite far to begin with, to get everyone on the same page, let's begin with something that's quite near, dear, and familiar to all of you here, and that's, of course, your laptop that you're logging in from, which can nowadays log into a cloud facility and control a quantum processor there, or maybe it's sitting next to your Dill fridge in your lab, which itself houses a cryogenic dilution environment, such as this golden chandelier depicted here. And at the bottom of the chandelier is, of course, the only quantum thing in this whole device so far, and that's the quantum processor, the quantum chip and device. The question is, how do we design, analyze, and understand the physics as well as the engineering of the quantum part of this device. Well, one way to begin, or one step you have to certainly think about, is the physical layout of the device. You have pieces of metal on chips, sapphire, silicon, etc., and they have some geometry. But to first order, the physical layout implements some kind of electromagnetic resonance structures, not unlike maybe the microwave ovens you have in your kitchen. To first order, we can use classical analysis techniques that have been well established, and we can leverage a lot from semiconductor industry and so forth. However, to go to the next step of the analysis, to really understand what's quantum about this device, this is where the departure between classical and quantum begins. And at this point, typically what we have to do is take the output of some semi-classical electromagnetic analysis, bridge the classical to quantum gap in order to understand the Hamiltonian that describes this physical layout, whether it's a single system or a many-body interacting coupled system. So that can quickly get tricky and more complicated. And of course, here with the Hamiltonian, we have to not just be able to write down the Hamiltonian, we have to be able to reduce it, diagonalize it, understand its wave functions, shape them, tailor them against noise, and engineer them. And ideally, you have to do this once, or maybe ideally you can set, here's my qubit frequency, couplings, and so forth, give me the layout. That doesn't really work. In practice, what one has to do is to iterate in this process over and over and over again until you have tailored the physical layouts enough so that you can attain the quantum Hamiltonian and dissipation parameters that you would want. So back in grad school, this would take me quite a lot of time in my life, almost months to get one device out. So overall, the goal here is to really be able to streamline this, automate this, and reduce that time, and make this as easy as possible so we can focus more on the creative aspects of the design. Now, this problem is quite central to the entire development of superconducting quantum devices. And so there are a number of quantization methods, or methods to bridge the classical to quantum gap, that span from fast, simple methods that have been around for a long time, such as the lumped equivalent methods, to methods that are more sophisticated, that use a mixture of quasi-distributed and lumped structures. And also more recently, within the last 10 years, to full wave methods, methods that can capture the full complexity and diversity of Maxwell's equations, the material properties, the exact geometries, and so forth. These include the impedance approach, or BBQ, black box circuit quantization, and the energy participation ratio approach, which can tell you about both the Hamiltonian and the dissipation. So there's a suite of different techniques that one typically has to use, and there isn't one to rule them all. Rather, we typically move in gradations of complexity from using lumped to using more full wave simulations. And it's also very thrilling to see that over the last some number of years, there have been more open source packages, starting with PyPR and QCat, now SE Qubits, and now Qiskit Metal, which aim to capture different parts of this process. With Qiskit Metal, we actually aim to capture the entire process from idea almost down to fabrication, and be able to implement all of these methods. Actually, I think at this point, they're almost all implemented in the code to various degrees. Now, if you'd like to know more about the field and more about different methods and sort of what the state of affairs is, I can recommend a few of these introductory and review articles. I'll just leave this here. You can take a screenshot later. But the big picture here is, to simplify things a little bit, is we have a chip. It has some physical layout. Maybe it's a 3D chip, maybe it's a planar chip, maybe it's something else. Somehow we need to bridge the classical to quantum gap and be able to express its Hamiltonian, its wave functions, maybe the complicated topology, and go back and iterate this. So we'd like to have a very tight feedback loop in order to be able to quickly find an optimal design. A little bit more specifically, we have to be able to also think about all the different components on the chip and simultaneously engineer quite a few things. So here's an example of a chip from IBM Quantum from a few years ago. Let's look at what it has. There's a substrate which has dielectrics metals on it. There are Josephson tunnel junctions, which provide essential nonlinearity. Of course, there's readout structures, qubit structures. What do we need to design? Well, for one, we need to design the geometry and topology of all this, the frequencies and harmonicities, qubit-qubit couplings, the spurious qubit non-local couplings, the readout frequencies and couplings of the different structures. Overall, the many-body Hamiltonian, the input-output couplings, the radiation dissipation per cell limit, spurious modes, sample holder modes, the loss budget due to dielectric scenes, and so on. In other words, you don't need to understand all of these, but there's a lot of different simultaneously conflicting demands that need to be optimized. So let's see how we can go through this process by example, using the framework of Qiskit metal. So let's lay out, analyze, and optimize a 4-qubit quantum processor. And to make this as hands-on as possible, I'll start very detailed by saying you can go to a GitHub page, scroll down, you'll find an installation YouTube video, which you can follow to set up a code base. It's an open source project. And after this, we can jump into actually creating some transmon qubits. So let's start with an initial layout. You can guess something. We can create our favorite transmon qubit, for instance, by looking at the library of built-in commonly used quantum components that one has within Qiskit metal. If the component doesn't exist that you want, if you're creating a new qubit, a 0 pi or whatnot, these are readily addable. Then one can kick up the metal GUI, which can show you what you actually have. If that's a bit too code-worthy, you can go to the documentation page at this website, and you can look at the library of growing components and sort of pick out your favorite, let's say, transmon qubit. In my case, I'm going to select this particular floating transmon qubit. So if you click this, you can expand and see a very sort of nice and detailed help file that walks you through how to create a transmon qubit, what it means, what its properties are, and how to shape it. And having done that, we can look at what that particular transmon qubit now looks like in its physical layout implementation here. So here's a pocket transmon. There's 2 metal islands connected by Josephson tunnel junction here, just for simplicity, represented as a rectangle. And in this particular transmon, we've also added 4 coupling pads that can couple to neighboring readout bus structures, charge lines, etc. In metal, you can think of each of these components as a instance of a class, and a bit like a P-cell, except it's a dynamic P-cell, so you can, in real time, modify all of its properties through the GUI or through the API code. And each of these polygons here you see has a number of other features that are going to be needed and associated with simulations, such as are these junctions, are these metals, dielectrics, and so forth. And I'll get to that in just a minute. If you are not used to looking at transmons that look like squares, but you like the cross-looking version of the transmon, of course, that's also built in, and you can add couplers and sort of modify it. It's fairly dynamic. I'll just point that out. Now, let's say that we want to take these building blocks and place them in our layout and create a 4-qubit chip rather quickly, so we can rapidly prototype it and see what happens, and then iterate on that. So here I've placed 4-qubit chips by just taking that building block and placing it in 4 different places. Then you can see that each of these transmon qubits has these connections or pins, such as qubit 3 has a pin A. You can specify in Qiskit metal that qubit 3 pin A should be connected to qubit 4 pin B, and then you can use the built-in auto-routing algorithms to say, give me a coplanar waveguide of a length such and such, or that will give a resonant frequency of such and such, and that will auto route with a lot of flexibility a coplanar bus coupling resonator between qubit 3 and qubit 4 here. So we now have a 4-qubit chip. And we've interconnected the 4 qubits. The next step in the design phase is to also create input-output routing so we can get signals on and off the chip. So here's an example of that, building that up in the Qiskit Metal visual interface here. You can use the predefined input-output components, which are these launchers, coplanar waveguide launchers. And we've used a different routing coplanar waveguide component to connect the different launchers to sites on the qubits, so we have some charge lines. If you also take a look at the documentation and examples, you find out a number of different qubit chips that show different architectures. So we can take whether it's cross-mons connected to qubits using bus coupling, or if the architecture you have in mind is a direct coupler between 2 transmon qubits or 2 flux qubits. You can either use the predefined features, or if it doesn't exist, you can join the Slack channel and we can help you sort of set that up as to how to do that. So here's an example of a different chip. So kind of to wrap up the layout part before we dig into the quantum analysis part of a quantum chip, I'll mention that as these chips get a bit more tricky and complicated, we're also building up the engineering part, the physics part, and also the routing part. So if you have 2 transmon qubits, such as depicted here, and you want to connect this particular pin to this pin while avoiding a collision of the coplanar waveguide with this other transmon, we built in some A-star graph-based algorithms that can do some basic collision avoidance and auto routing with enough flexibility so that you can do some more interesting features like that. And if you're really interested and you love coplanar waveguides and doing planar chips, you can really go crazy with with the various devices you can build. So having touched on and covered the layout part, which is a bit more like a traditional layout tool, but is quite flexible and specialized to quantum analysis, I'd like to dig a little bit deeper into how we're going to use that to really now understand the quantum physics and the electromagnetics of this particular quantum processor. And so this is really where Metal starts to make more sense. Its goal is to fill the gaps that don't exist in the conventional tools. So we don't want to reinvent the wheel here. Instead, we're very focused and interested on how do we cross the classical to quantum bridge, the gap between these pieces of metal and the quantum Hamiltonians that they somehow support. Coming back to the landscape of different quantization techniques, going all the way from Lunt, which are very fast methods, to things like the energy participation ratios, which I'll explain in more detail in a second. In Metal, we've started building in a library of quantum analysis that actually represents sort of the full spectrum. So here's an example of the capacitive analysis, which we'll touch on and explain in a minute. The eigenmode approach is also built in, so you can quantize a chip by doing eigenmode simulations of parts of it. And you can also use the scattering matrix, Z matrix or Y matrix. You can do simulations, either classical to look at maybe crosstalk and optimize that, or to use something like the black box quantization approach to extract out the Hamiltonian. For definitiveness of the discussion and example, let me zoom in on the eigenmode approach and focus a little bit more on now the physics of actually what's happening under the hood at a high level picture. So I'll start with the quantization of Josephson circuits based on energy. So you can take a look at this archive reference, or if you can see my dissertation. This was work done at Yale, which is now extended. If you remember the slide with all the questions of what needs to be designed, what you'll find out in this paper and in this dissertation is that the solution of all of these questions about both dissipation and the Hamiltonian, almost magically, if you ask me, reduces to the simple question of asking, where is the energy? In other words, what fraction of the energy of a mode, such as a qubit mode or a resonator mode, denoted by P, is stored in the nonlinear or dissipative element, such as a Josephson tunnel junction or maybe a lossy dielectric. And this is a number between 0 and 1, which can tell you both, if you have all the energy participation ratios or P sub j's, those can tell you the full quantum Hamiltonian of the transmon coupled to a cavity or coupled to a fluxonium or other more complicated structure, including all the many body interactions and so forth. And if you look at the same exact type of number, which is this number between 0 and 1, you can instead extract the dissipative parameters of the circuit. So how does this work? Well, at a high level, let's look at what the Hamiltonian of a distributed system, such as a chip, looks like. And maybe I'll start with a simple kind of pop quiz fun trivia question, which is, suppose I have a linear system. It's an electromagnetic system. Maybe there's some materials in here, but let's just say it's a box, because boxes are simple. Can you tell me what the Hamiltonian of this box looks like? I think probably just about everyone here can tell us that the Hamiltonian of this box is simply a sum of bosonic modes. It's just the number of harmonic oscillators. You can think of it that way. From m equals 1 to probably infinity. And each mode has some ladder operator, A and A dagger, which define excitations. And there's a frequency for that mode. Now that's probably fairly simple. Now, what if I have a very strange cavity? Maybe it looks like this. Maybe it has all kinds of dielectrics and materials and metals and weird things in it. What is it? What is its Hamiltonian? Well, even for the strange cavity, the Hamiltonian has the exact same form. Now, the relationship between the frequency and the exact geometry is very complicated, but the form of the Hamiltonian is always the same. And for a linear system, we can always use the classical electromagnetic simulation to extract that. So what happens if we now add in nonlinear dipoles, such as Josephson tunnel junctions? Well, let's play a trick to make our life simple. Let's take the nonlinear dipole element, may it be a squid, a snail, a Josephson junction, whatever it is, as long as it can be described by an energy function of the magnetic flux across it, you can partition it conceptually into a linear piece plus a bunch of nonlinear pieces. Now, maybe it's important to emphasize that this is only a temporary step. This is a step that is not, in a sense, final. Instead, the nonlinear piece will be combined later with the linear piece again. So we're not losing any information at this stage. Suppose I then stick these nonlinear dipoles and just the linear part of these nonlinear dipoles in some sort of strange cavity. And ask the question, what is the Hamiltonian of this strange three-dimensional Maxwell thing? It's the same, because it's a linear system. It's the same as the other simple systems. Then you might ask, that's really nice, but how do I now put back the nonlinearity? Well, it turns out that for any such microwave circuit, you can always break up its full quantum Hamiltonian into a linear piece and a nonlinear piece. As we're now all experts, the linear piece you can always write down as some sum over simple harmonic oscillators. Nothing tricky there. What is tricky, of course, is what basis these operators are defined with respect to. This is second quantization with respect to the normal mode basis of the linearized Hamiltonian. But it's only a basis change. What is more interesting is what's the nonlinear part of the Hamiltonian. Because everything in the linear part of the Hamiltonian, which essentially boils down to just omega m, just the mode frequencies, that can be found by a classical eigenmode simulator almost trivially. They're really, really good at doing that. What's not so obvious is what happens with the nonlinear piece. Well, the nonlinear piece is some known function, it's known because it's the Josephson potential energy, of the operator that defines the magnetic flux across the Josephson tunnel dipole. Now that operator is unknown. We don't know what that is yet. So let's look at it. That's really the only thing that we don't yet know, the quantum flux of the nonlinear dipole. Let's take the example of the transmon qubit we looked at earlier. This operator refers to the magnetic flux fluctuations across the terminals of the Josephson tunnel junction, roughly the voltage drop here, related to the voltage drop here. It turns out that that flux is just a linear superposition, just a linear combination of the voltages or of the magnetic fluxes of the quadratures, if you want, of all the different modes of the system, weighted by a coefficient called the 0-point quantum fluctuation. It's a real number. The 0-point quantum fluctuations tell you how much the magnetic flux across the junction fluctuates, what is the standard deviation, due to the participation of the junction in mode M. So due to mode M. In other words, what we need to find out is what is the 0-point quantum fluctuation of the phase of junction J, if we have many junctions, due to mode M. And at this stage, that's the only unknown parameter needed to reconstruct the quantum Hamiltonian. It turns out that this 0-point quantum fluctuation can be completely determined by looking at what fraction of the energy of a mode M is stored in junction J. So it boils down to energy. And energy is something we can easily work with classically as well as quantum mechanically. And you can almost derive this on a napkin. Actually, you can. It's a couple of lines of algebra. But the bridge between the classically calculable parameters, which are the mode frequency, the Josephson energy of your nonlinear dipole, and the energy participation ratio, which is how much energy this linear inductor here will suck up from the mode of the qubit, say, or the mode of the resonator. These three classical parameters are all you need to cross this classical to quantum boundary to find the 0-point quantum fluctuations of the Josephson junction J in mode M, which is this phi squared over mj. So on the left-hand side here, we have purely quantum parameters and numbers. On the right-hand side, we have things that we can calculate classically. Both P and M we can simulate in regular electromagnetic simulators and are well known. You might ask, what happens if I have a flux biased condition? What if I have a flux tunable device? If I have biased parameters in various combinations? You can repeat the same process. You have to simply do it at the operating point. Maybe this is a bit technical, so I'll refer you to the paper for details. But the short story is you can do it. Okay, so maybe that's a bit on the physics of how you would apply the energy participation thinking to a general circuit. How do we now take that knowledge and apply it to a very specific design? Let's come back to our design here. What you can now do in Qiskit Metal is to use the rendering function. This allows you to take the design you see in Metal and export it in real time to a simulation backend. Here we've used what I've been using for some time, which is ANSYS HFSS. You can either render the full design or you can render part of the design. Here you see the Metal window in the background, and Metal is now rendering in ANSYS HFSS. This is basically just building on PyPR at this stage, just uses those functions. And from there, you can run simulations of the different electromagnetic properties of the circuit. So you can do this real-time rendering, whether it's in HSS or Q3D or different, ideally we'd love to be able to do this in the future in ADS or Sonnet and so forth. So it's set up in a general purpose abstract way. And in this rendering, we've tried to build in best practices and all the tedious things that usually you have to do by hand, such as placing the boundaries, whether things are perfect electric conductor or other electromagnetic boundary conditions. We've built in best practices, such as on meshing, using native curves for the particular way that coplanar waveguides, for example, are made. In the case of electrostatic simulations, auto finding the nets of the device and also running the analysis. And in particular, taking very careful caution on what you do when you break up the chip into subdomains, which you analyze for particular parts of your analysis. Because you don't usually want to simulate the entire chip at once. That's quite complicated. Generally, you use the analysis method on subparts of the chip. So you might break out just these two qubits coupled by coplanar waveguide. And then the question is, well, what do you do with the way you break it? And so there's a lot of flexibility for the different methods that we've built into Qiskit Metal, whether things are open or short, depending on how you've set things up. So with that, you can run the analysis of the subcircuit, which can give you which has this built-in best practices, native optimized curves, gives you smaller memory. And from there, that leads you to, in the case of an eigenmode simulation and the energy participation ratio, eigenmodes of the cavity. So here I've depicted a 3D cavity having a 3D transmon chip. You can also do this, and we do this for planar chips, such as this transmon qubit coupled to the coplanar waveguide. I just tried to illustrate that the setup is in principle general here. Now, what the eigenmode of this cavity looks like is just the oscillation of the fundamental T101 mode of this 3D cavity. You can see the electric field oscillating back and forth. It's highest where we have red, indicating the highest density of electric field lines, and blue means almost no field lines. If you zoom in to the superconducting qubit chip on here, it has two metal pads connected by Josephson tunnel junction on top of the substrate. If you look at the Josephson tunnel junction here, it has a current that's going through it even inside the cavity mode because of the hybridization. And by looking at how much energy is stored in that Josephson junction as a fraction of the total inductive energy stored in the mode, which is just 1/2 Li squared divided by the total inductive energy, where I is the current across this mode. And you can construct these energy participation ratios. You can use them to construct the 0-point quantum fluctuations, which in turn give you the full quantum Hamiltonian. And you can use that to create the Hamiltonian, diagonalize it, and extract the parameters. So if you do something like metal.analysis.analyze, you can analyze, say, this 2-qubit coupled device here, and you can look at the convergence of the frequency of the qubit, which is this red line, or the anharmonicity of the qubit, which is this blue line, as a function of the adaptive pass number of the simulation, because simulations always give you an answer. So you'd love to be able to be confident, at least self-consistent, in the simulation that you've given and done. You can also extract things like the cross-curve between the two qubits or other structures as a function, again, of how well the simulation is converged. And from there, one can go on and once you have knowledge of full Hamiltonian, you can extract or understand higher order multi-wave mixing processes, so many photon interactions or driven processes. So you can take a look at the EPR energy participation ratio paper for sort of more details on that. The interesting thing with the energy participation ratio is that the way you calculate the Hamiltonian based on participations is the exact same idea that you use, the exact same calculation, in fact, that you use for calculating the dissipation budget. So you can find out how much a capacitive element in your circuit leads to dissipation. What is its participation? Based on these, these are well-known, sort of very, very well-established methods for calculating the lossy energy participation ratios. And I won't go through all the math here, but you can take a look. This is all built in, essentially. You can say, give me this participation. Once you've tuned by iterating the design, you can export to a format for fabrication, such as GDS. There's a GDS renderer here. If you click GDS, it walks you through what you want to export, a number of things like, do you want a positive mask, a negative mask? Do you want tolerance that's such and such, etc. So you can always customize that. And out comes the GDS file for fabrication. So at this stage, we've created our Transmon 4-qubit chip. We've exported it to tuned it in metal, exported it to GDS. You might ask, how well does this do? So let me maybe first give you the energy participation ratio version of this. And this is data on 3D devices. This is from the Yale paper. Over 9 different samples on 2 3D transmons, flip chip, whispering gallery mode, qubit, as well as a di-transmon waveguide device. The short story of the slide is that the measured versus predicted energies of the Hamiltonian of these devices for both frequencies of the modes as well as self and cross nonlinear coupling. So these are self curves and cross curves and harmonicities, and also very large 200-300 megahertz cross curves between two devices. You can get very good agreement at the level of a few percent. At the level of very small couplings, these are dispersive shifts on the order of a megahertz typically readout, and very, very small readout, very small ZZ couplings or dispersive shifts between qubits. For instance, you can get, sort of 5-10% agreement, and you can actually do even better if you include things like the intrinsic Josephson capacitance in here as well. More recently, now done with the metal automation, you can look at, again, the theory versus experiment. So this is done for, this is data that corresponds to this paper we put out recently on dynamic circuits. So you can look at now planar devices. This is from my notebook where I've looked at 10 different qubits and have used the metal analysis here to extract their frequencies and harmonicities and so forth. And we can compare the measured versus predicted qubit readout cross curves on planar devices that look more like this using a lumped method, which is not the most advanced lumped method. It's sort of a more standard approximation lumped method. Measured versus predicted dispersive shifts here give about 20% agreement on this very small parameter. So not bad, but maybe not ideal. If you use the energy participation ratio method, we found about a 4% agreement between theory and experiment. And if you're wondering what happens if you use the impedance-driven simulation, we found a 7% agreement between theory and experiment. So roughly the same as EPR, but maybe EPR that's slightly better, maybe within the error bars. The final point about the energy participation ratios is these universal properties that tell you that the 0-point quantum fluctuations are not actually independent of each other. Instead, they're monogamous in some sense. And really what's monogamous is, the way I think about it, is the energy participation ratios. Maybe I'll explain it by starting with this joke. This has become a bit of a joke. There's these 4 commandments of EPR. The joke is that EPR is neither created nor destroyed. A Josephson dipole brings exactly 1 unit of EPR to the circuit, no more, no less. And a dipole, which is this nonlinear element, must spread necessarily all of its energy participation ratio across the modes of the circuit. It can't hoard any of its own. And on the other hand, a mode can accept at most 1 unit of energy participation ratio, no more, from all the junctions. So if you want the sort of more mathematical version of these commandments, the EPR is bounded between 0 and 1. The sum of the participations for a given junction across all the modes is precisely unity when you take all the modes of interest into account. The sum of the participations across the junctions for a given mode must be less than 1. And finally, the participations also obey a certain orthogonality that's given by this expression. I'll refer you for details to the paper. And so that wraps up this approach using the energy participation ratio. So I can give you a summary of the big picture, which is you start with a classical model, you linearize it for a second, you find its eigenmodes. You don't need to do any impedance simulations. From the eigenmodes, you have the modal frequencies of the linear modes. You calculate also the energy participation ratios, the signs that are associated with these. which allow you to reconstruct the full quantum Hamiltonian, including potentially a dissipation budget, and then you iterate in this loop back and forth. And so the EPR approach describes any order and strength nonlinearity in principle. It also describes composite nonlinear inductive devices. It's based on a first principle derivation. My claim is that it has zero approximations aside from truncation of the modes. So I'm having a fun debate here with Jens Koch about this, and I'll let you know the outcome. And it's fully automated, initially in PyPR and now in Qiskit Metal, which builds on that. So what are the limitations? The limitations are that in practice, you might not be able to simulate every single mode you want, or if you do, then you might have you have to truncate your basis for diagonalization of the Hamiltonian. So that summarizes the approach with the eigenmode. To give you a more concrete idea now of one other key approach that is not going to capture as much information, it's not going to tell us as much about dissipation, it won't tell us as much, it won't give us as much accuracy perhaps, it won't be applicable to 3D as eigenmode is, but it's quite good and quite fast for especially planar devices, so it can give you, most of what you want right away. I'm now going to show you a recent result and how to use metal on a lumped structure or quasi-lumped structure. So that's this approach. The details of this are explicated in this paper that came out recently on the archive. But the goal here is to have an approach that's fast, modular, and precise. We don't really want to simulate the entire chip, but we want to be able to break it up into individual blocks that we can simulate independently and bring them together without any loss of information, ideally. So the goal in this particular approach is to break up the chip and be able to say that we can write it as a sum of a system Hamiltonian plus interactions, where the system is really just the standard sum of small known building blocks that each commute. And there is an interaction Hamiltonian, which we'll write in a pairwise bilinear form like this, where just every system could be coupled in principle to every other system, where these operators belong to two different systems. Now that seems sort of simple at first sight, but in practice it's quite tricky because of the actual way that you define these systems. If you look at the couplings that mediate interactions between different, say, qubits on a chip or buses, these Hamiltonians here are not independent of each other. While they're independent at the level of Hamiltonians, at the level of physical design, they could actually be heavily dressed by couplings across them, and they can thus depend on each other. So if you change the parameters of one piece of metal, one device over here, that can actually affect what happens to a neighboring structure in principle. And to extract these Hamiltonians and the couplings between them for the general physical layout, this could include the case of very large couplings that are so strong that they're non-perturbative. They renormalize the modes by gigahertz. They're non-local. They have constraints. We have to be able to eliminate also a number of idle degrees of freedom that are at zero frequency, essentially. So we have to take that into account. And there are other more subtle CQED effects like the A-squared diamagnetic contribution and so forth. So we'd like to be able to do this systematically and in a general way. And so that's what this paper is about. The method here that's implemented also in metal breaks out one part of the chip. You can represent it by an effective schematic or circuit model. You can pick within that native systems that you can isolate as things that are familiar building blocks. Maybe this transmon qubit, this loaded transmission line. There are certain conditions. You can't pick anything because it has to be able to admit the renormalizations of the rest of this, of the dressing due to the rest of this network. But basically, it's the building blocks that you're familiar with, such as transmon, fluxonium, etc. And then we have to be able to describe the interaction between these two systems as mediated by the entire remainder of the circuit, which is this orange box. And ideally, we'll do this without any approximations beyond the lumped model. So the way that this works is we can zoom in on part of the chip that we've designed in metal. we have this transmon qubit here, coupled to, say, neighboring qubits. There's a readout resonator. These are simple building blocks. Each of them is well understood in isolation. And we'd like to be able to understand their Hamiltonians. Now, in isolation, those Hamiltonians have some parameters, but when they're coupled to all these neighboring systems, those parameters get potentially severely dressed. So we'd like to know what that dressed Hamiltonian H1 is of this readout in the presence of all this other metal, H2 in the presence of all this other metal, and so on. And the way we do this is by partitioning the physical layout into independently simulatable cells, such as sort of depicted here. Each of these cells, which corresponds to the physical layout and is a different partition than the system partition, can be automatically rendered into metal. Here we've used ANSYS Q3D to do an electrostatic model of this part of the device. It's just a single transmon with a couple of leads, which we've included. All the material properties are automatically added. Metal can then run a simulation and identify the galvanically isolated islands. It can extract the capacitance matrix that the circuit has and combine it with the linear, the nonlinear inductive elements here, such as this junction, which would sit between pad 0 and pad 1. Pad 0 is this island, pad 1 is this island. And the graph here represents the capacitive links between all of these different nodes of the circuit. So each node corresponds to one little dot in this circuit. And some of these dots belong to different systems. Anyway, all of this is automated. But from this full network, one can carefully construct the full Hamiltonian of the coupled system and then obtain the dressed effective Hamiltonians of the transmon, the different loaded transmission lines that belong to the coupled structures, as well as extracting out the dressed coupling Hamiltonians between the qubit and, say, this particular readout resonator, or the qubit and this bus resonator, and so forth. So from this, one can really reconstruct the details of the chip from the capacitive simulation, which is a very quick way to do the simulation. It takes a couple of minutes to run these. And I won't have the time here, unfortunately, to give you more of the detail of some of the fun and subtleties, but I'll just tell you how well does this work.
And Zlatko, can I just come in for 1 second? We have a bunch of questions that are piling up into Q&A. So I just let us know when you're ready to take a few, because I just want to make sure we can address some of these interesting items that are coming in.
Oh, perfect. Okay, great. I am running close to the end of my talk. I think I have about 10 minutes left. So maybe I'll just wrap up here and we'll take questions if people don't mind staying a couple extra minutes.
Thanks. Sorry, as I said, they're piling up here, so we just want to make sure we get into a few of these. Okay. And so I will turn it over. Carl is going to be our moderator for questions. So Carl, I'll turn it over to you.
Well, we indeed have many good questions. So a few of them are long. So let me go as slow as possible for this one. So one of the questions states that, as you anticipated, I am puzzled by some of your statements. There are questions about boundary conditions, and there are questions about the strength of anharmonious, I can't pronounce that word. Specifically, the phi variability does not exist in the case of Cooper pair box. And 2, if you write heavy fluxnoniums as HOSC and HNL, then low line states have pretty much nothing to do with edge states.
Yeah, great. This is a very good question. This is the same. This is basically the question that Jens Koch and I are going to have a nice, fun, heated debate about. I need to get back to him on that. But so he might be right. Probably he's right. He's a very, very smart guy. The question is about, if I understand right, the question is about, I think I made the statement that in the energy participation ratio method, you can get, there's no approximations in a sense. This Hamiltonian, the way you can think of it is that all we've done is taken the original Hamiltonian broken it up into two pieces, a linear and a nonlinear piece. There's no, algebraically speaking. We've done a change of basis, which diagonalizes the linear piece, and we followed through that change of basis on the nonlinear piece. And this is the result. So at the level of algebra, so nothing interesting has happened. Now that looks a little bit strange because it looks like we did a Taylor series. And here I've written it as a Taylor series, but this is not needed. This is just some nonlinear function. Things like the charge dispersion are interesting. They're certainly not the easy thing to get using this basis, because we've used the harmonic basis, not the Cooper pair basis. And Michel Devray recently wrote a sort of beautiful article on this, on the junction flux versus Cooper pair basis. Sorry, treating the junction flux as either a wrapped or an unwrapped variable. And also in the EPR paper, we have a discussion. You can get the charge dispersion using this method. So here's a slide which shows you that in a very inefficient way. So I'm going to use many levels, but you can do that. I have a big computer. I can reconstruct for, say, a transmon qubit, which is one I measured here at 6.5 gigahertz. It has 300 megahertz in harmonicity, so it's EJ over EC of 50. I can find the expected dispersion relation by including enough higher level modes in the system. Higher level Fock states in the system. So if I look at the eigenvalue number as a function, the eigenvalue energy as a function of the eigenvalue number for the Hamiltonian of constructed from the energy participation ratio, and I've included something like 8,000 simple harmonic, no, I think this may be 800 harmonic states. You see that there are about 25 energy levels at the Hamiltonian here that are all nearly the same energy. Then there's another 25 nearly the same energy, another 25. And what you're seeing here is really the different levels of the transmon. Eventually, when the energy is high enough, you have this quadratic free particle behavior of the, this is energies above the well in the transmon qubit. If you zoom in to, let's say, this first two levels and you look at the transition frequencies between them, you'll notice that as a function of the intraband index, these are just Bloch bands, as a function of the index of the eigenvalue within the band, there is a dispersion. And if you look at the size of the dispersion, this is exactly the charge dispersion. And it reproduces the sinusoidal behavior as a function of the quasi-momentum or the charge offset. So each of these different points here corresponds to a different charge offset. If you look at the wave functions that are associated with each of these levels, the ground function, the wave function of the lowest energy level is this orange function. It's basically the same Gaussian wave packet that you normally have in your well down here at the bottom, copied over a number of times, because effectively what you're simulating here is a cosine periodic potential, but it's on an open line, and at some point you just truncate the edges because you've truncated your Fock levels. So it's not periodic, excuse me. It's just it's a finite length approximation of the continuum. So you can recover most of these results, like the charge dispersion and so forth. And it's not efficient in this way. You have to use many levels. I wouldn't, advise you maybe to do it in this way. But in principle, there's no information loss. You haven't made any approximations yet. You can still get the information out. You've simply just used a different basis. It's maybe a little hard to explain in a few slides here, but I'd be happy. You can write me an email and I'd be happy to chat more about it.
All right, wonderful. I'm looking at the time, and I do want to get one more question in before we log off. And for any questions that we miss, we'll definitely try to get those answers and post it on the C2QA's page for those responses. Now, another question is about how did IBM choose the topology and routing for the device it did? Which factors mentioned in the slide, the one with all the conflicting objectives listed, did IBM consider during the process?
Yeah, this is a great question. So maybe let me give you an example. This is actually a device that we recently designed with metal. and fabricated. And this is going to University of Tokyo, Tsuro. It's called the Tsuro device, the 5-qubit device. So this is the first device made and fabricated with metal. Sorry, designed with metal, help and fabricated, and we're going to have data on it soon. This is based on one particular architecture of transmon qubits with bus couplers. That's been the bread and butter at IBM for some time. But it's not in any way the only thing. Recently, I'm quite excited to share that we heard from Chris Warren and from Jonas Bylander's group at Chalmers that they've reproduced their standard version of their standard quantum devices with Qiskit metal and sort of designed this particular device with the help of Qiskit metal. It's an 8-qubit hanger type of device that looks like this. They've simulated it with this kind of interesting circular transmon version. And Chris recently shared with me that they've now cooled it down and measured it just a couple of weeks ago. And here's the resonator spectroscopy of the 8 qubits, and they've measured the qubit amplitudes and are comparing the data to the experiment that they've now done with this. So they have a very different architecture with very different parameters. So metal is supposed to be quite general purpose and generic. So there, the reasons for choosing whatever I chose there were not based on metal. Those were just based on designs that I like, that I'm more familiar with, or that we've done, for instance. And I guess more recently, it's maybe interesting to also note that we did basically the first quantum hardware hackathon that I've heard of anyway. And we had a different architecture specified. It looked like this. There was 2 qubits coupled by these buses with these readouts. And we had 4 teams of sort of 4 to 6 folks each that had to design these devices. These were students from Korea. Many of them were certainly very much newcomers to the field. They hadn't ever done this before, or designed quantum devices. So it's pretty exciting that in the competition, in just 2 days, they were able to go from scratch to actually making these devices to spec using the metal layout and analysis and simulations, some screenshots of the design from that event. So, that makes me feel both very happy that they were able to do this, and especially with this tool, which by the way is very much an open source early alpha, lots of bugs still to sort out. But at the same time, you spend like months doing this, so it does make me feel a little funny about that. So maybe that gives you a bit of a perspective. You can go crazy. You can make whatever design you want. This is an example of something rendered with metal that's just more insane. So hopefully that helps answer that to some degree.
I am muted. All right, thank you for that response. All right, I noticed that we are over time. So for any questions that we did not get to, we'll be sure to document those questions and have those answered. So again, I want to thank everyone for this wonderful presentation. Thank you all for joining us. And we do hope to see you at the next C2QA Quantum Thursday. Please have a wonderful afternoon.